Hello, we are Team 3 and I'm Juno with Subin Kim and Igor Alentev. We are going to discuss about our project Doctor Strategy. Our proposal is based on the paper Doctor Strategy, Model-Based Generalist Agents with Strategic Dreaming. The key idea of Doctor Strategy is that it is aiming to do goal condition reinforcement learning starting from scratch with pixel-based image as input. By starting from scratch, it means it will try to explore and learn the environment on its own without any information. This ability is very important for generalist agents that needs to learn and achieve various goals in an open-ended way. Doctor Strategy is based on a model called Dreamer. Version 2. Dreamer is a model-based RL algorithm where a world model learns the traditional dynamics of the real world and can simulate upon latent states in parallel manner, which increases sample efficiency. Another model-based algorithm, Lexa, uses Dreamer to explore and learn random goals during training. By using the trajectories from the simulation of the world model, Lexa trains a goal-conditioned agent. Built on top of Lexa, Doctor Strategy adds a divide-and-conquer approach leveraging the structures of latent landmarks. This can enhance the efficiency of the dreaming in MBRL and promote better exploration and achievement quality of a generalist agent. For instance, riding a train to reach certain landmark and then riding a taxi to navigate detailed roads is much more easier than trying to reach there by car from the start. We can say that riding a car from the start and having to memorize different paths as one is Lexa. We use this strategy to divide state space into clusters and evaluate only the cluster centers to get necessary values, such as exploration potential and distance to the goal.
There are three agents: Highway Policy, Explorer, and Achiever. During training time, Doctor Strategy explore the environment and gather sample trajectories using Explorer. The Explorer is trained to explore areas that is most unpredictable. We find this out by using ensemble of neural networks, where the different network tries to predict the same state. If it has high variance, we conclude this is the most unpredictable state. Highway policy is used only to reach discrete landmarks, and the reward is the distance from the current state to the target landmark. Achiever is trained to reach the final goal, and we train a temporal distance predictor to give this reward. A temporal distance predictor is given two states and tries to predict how many steps is needed to move in between. To be more specific, during exploration shown in section 5, Doctor Strategy evaluates only the cluster centers and start exploring starting from the landmark that has the highest exploration potential. During test time shown in section 6, Doctor Strategy finds the nearest landmark to the goal and uses highway policy to move towards the landmark, then reaches the goal using the achiever. This way, highway policy only has to learn finite set of cluster centers, and Achiever also needs to reach only the nearby destinations shown in section 4. Doctor Strategy calls this way of training as focus sampling, meaning that the Achiever doesn't need to know every navigation route to every state, but instead just needs to focus on nearby destinations. Doctor Strategy experiments in three environments, which are 2D POMDP navigation called Mini World, 3D maze egocentric navigation, which is called Memory Maze, and Franka arm manipulation, which is called RoboKitchen. Doctor Strategy tests variant versions from these three environments, where they test 9 rooms and spiral 9 rooms and 25 rooms in Mini World, and each room size is 15 steps by 15 steps compared with the agent's 1 step. They also test different maze structure and sizes, which are 7 by 7 and 15 by 15 in Memory Maze. We can consider these environments as very large spaces because the agent is given POMDP or egocentric view, which is restricting and also has large room sizes. The results show that Doctor Strategy was able to reach a very high success rate compared to other baselines such as Lexa and GC Director. In RoboKitchen, it shows comparable results. In larger state spaces, such as 25 rooms and 3D maze size 15 by 15, the success rate itself is lower due to the complexity of the environment.
Original paper suggests interesting idea of training highway policy to reach some goal landmark. However, it doesn't ensure the optimality of the found path, only reachability. This is why we would like to suggest some hierarchical structure which will allow to split the task into several subtasks, which will produce overall better result. If multiple skills could be connected and recombined appropriately, it would be possible to solve various tasks in a more generalizable manner. For instance, splitting the task into subgoals will allow us to have composable structure, which would help to reach various tasks within an environment. Moreover, we will have explicit control over the algorithm and produce more optimal results instead of relying on end-to-end solution. Finally, chaining allows not only to split the goal into subgoals, which are inherently easier to solve, but enables recursive decomposition, further optimizing the solution. To make this improvement, we need to split it into two separate parts. Firstly, we need to define the optimality, and then find the path according to this definition. For optimality, we want to define the weights of the edges, transitions between the landmarks. Then these subgoals will be chained into optimal path. There are several approaches, for example, number of transitions to move from one landmark to another. Alternatively, we can cheat and use real-world complexity to check the task's feasibility. Also, several more complicated approaches include dynamically computing the weights during the imagination rollout and creating layered VQVA structure with different number of clusters, which will help us to estimate the weights stochastically. Path planning itself includes different algorithms, deterministic, heuristic, and even stochastic. The choice of the algorithm heavily depends on the weight function, so these two parts should be considered in tandem. Our initial guesses for efficient algorithms include some simple algorithms like OBFS, DIAL, and some more robust algorithms like Dijkstra, because it will allow us to adapt the task complexity to environment in case of sparse or dense graphs. And also, we want to consider using algorithms from A-star family, as they provide some heuristics and stochasticity in case we'll need it. And several other algorithms might be considered. Finally, we would like to talk about the timeline. Our timeline is split roughly on 4 parts. Firstly, we want to replicate the results of the paper with some basic code and examples working, which will take approximately 1 week. Then we want to check how good clustering and this baseline solution is. And then we want to start implementing weight functions and checking which of them suits the task best. And we most probably will need 2 to 3 weeks to do this. And when we start understanding the weight functions, we will implement the optimal path planning during the remaining 2 to 3 weeks.